in this case, which we are discussing, is that the load is now not a point load. Although I have given this under different topic, this is the same concept. The only difference is the load applied is not a point load anymore. It has been distributed along the area of the, or the along the length of the beam. How can we consider if there's a distributed load denoted by, let's say a distributed load given by L, which is a function of the length. So let's say based on the, let's say, fixed end reactions, of course, based on the structural analysis theory, maybe you can recall for such a beam which has been fixed at 2n can be represented by loads. So this total load can be represented by breaking it to, let's say, nodal loads, where there are the total load can be described by two nodal loads given by WL by 2 at the very ends, as well as two bending moments described using these equations based on structural analysis theory. Yeah, so this the distributed load can be transformed into let's say nodal loads in this formation. So our attempt is to now use a certain, let's try to use a certain method and try to break down the total forces into total distributed forces into nodal forces. Yeah, so the intention is nothing but represent a distributed set of loads using a discrete loads. So the underlying concept is the work done by the distributed load along the, let's say, length or along the displacement field is equal to the work done by the nodal loads at the corresponding nodes. So this is the concept. So the work is the same. The work done by the distributed load is equal, should be equal to the work done by the nodal loads. That is the main concept. And using this concept, we can now, let's say, break down the total. Let's for the time being, let's apply there's a normal force. The field, this bar is subjected to a normal load given by Wx in this formation. I have, as I shown here, bar having two nodes, 1 and 2. And now what we would like to do is we would like to represent this using nodal degrees of freedom. What are the nodal degrees of freedom which we have to take into account? At node number 1, there are rotation and transverse displacement and the corresponding forces and moments. Similarly, at node number 2, there are forces and moments and the corresponding transverse displacement and the rotations. We now try to simply compare or equate the forces done by the distributed load and the forces done by the nodal force. So our concept is the work done by the distributed load is nothing but the distributed load. This is the load function multiplied by the transverse displacement function, and you need to integrate it along the length of the element from 0 to L. And this distributed work, distributed load can be should be equal to the discrete distributed work done by the load should be equal to the discrete forces, let's say work done by the discrete forces as well as moments. So what is the work done by the discrete nodal forces? It is nothing but at node number 1, the bending moment times the rotation. Node number 2, bending moment times the rotation. Of course, at node number 1, the shear force, that is F1 y hat times the displacement D1 y hat, F2 y hat times the displacement at D2 y hat. So this is the work done by the discrete forces, and this is the work done by the distributed forces. So by equating the distributed forces to the discrete forces, that is work done by the distributed forces and moments, of course, to the work done by the discrete forces and moments, we will be able to describe the distributed functions using the nodal forces, and M1 and M2 as well as F1 and F2 can be found. Let's do a force replacement example. Consider a simple beam element having a distributed load W, node number 1 and node number 2 having a length L. And now we would like to represent this distributed load using nodal displacement, so nodal forces and moments. So we assume this uniformly distributed load along the beam can be segmented into discrete loads in this way. How? This beam is subjected to nodal forces such that at node number 1 and node number 2, it is subjected to a bending moment and a shear force, and the corresponding displacements and the rotations are mentioned using the conventional signs or conventional terms that we just used to describe our equations in the previous sections. So what we do is we apply the principle of work equivalence by simply equating the work done by the distributed load is equal to the work done by the discretized force and node number 1 and node number 2. What is the work done by the distributed load? Integration over the length L, the force applied, that is Wx, and the transverse displacement given by V hat x, which is equal to the moments or the here I have sent mentioned the corresponding, I have written down the corresponding work done by the bending moments and the corresponding work done by the shear forces. The shear forces by the nodal forces, since they move in the transverse displacements or in the y direction, there's a certain work involved, and since due to the bending moment there's a certain rotations involved, there are certain energy or work involved in those components. So by applying these equations and applying the sign convention, we know that Wx acts in the negative y direction. We can simply mention it as minus W. And since we already know that so since by, let's say, we apply this equation here, and what you would really end up is getting an answer for the, let's say, an answer for the displacement function would end up get it in terms of if you can recall the displacement function which you described for V hat for in the which we just derived for a spring element having, of course, 2 nodes, if you can remember. You can simply substitute this value here to perform the integration. You know Wx is minus W, Vx, you know, you can substitute it here, and you can simply do the math to obtain the solve this equation which I have just shown here, equation number 3, to obtain, let's say, arbitrary displacements. And you can use this equation which you just derived and apply arbitrary displacements to check the validity of the equation. let's assume that, let's say, since we already know aware about the shape functions, we know whenever there's a, let's say, we can simply apply, let's say, this arbitrary displacement at, let's say, node number 1, and we assume, let's say, there's only a rotation, unit rotation, and all the other corresponding displacements to be 0 within the bar, within the beam element. We can reduce the terms and obtain equation for bending moment at, let's say, length L. You would end up in getting is minus WL times WL squared by 2. Similarly, to apply to obtain the, let's say, bending moment at node number 2, you can assume all the remaining degrees of freedom to become, let's say, 0. That is at node number 1, node number the rotations at node number 1, the displacement, transverse displacement at node number 1 to be 0, and only make the rotation give a unit value to the rotation. So because you are interested in finding the moment at node number 2, yeah, so you assume the rotation at the node number 2, you give a unit value and see, of course, the transverse displacement to be 0, and see what the result you get. You would end up in the same results that you get from a structural analysis theory. So similarly, by taking all the other, let's say, nodal displacement to become 0, you can find the shear forces acting at node number 1, at node number 2, and you would end up that getting these answers where you really comply with the equations you get from the structural analysis theory. So I have mentioned a note here. So if there's a load, the distributed load function, we can multiply this distributed load function using by the transverse displacement function, and of course you can integrate it into equation 3, and this is the result of what you get at the end. So the conclusion, what I want to say from this derivation is that by applying the work equivalence principle, you get the same results at the nodes which you can obtain also structural analysis theory. Yeah, so this is quite a powerful method. So before we wind up, just to get things straight, let's try to do a quick example to get familiarized with the solutions with this concept, so that you can you are familiar and you can work out problems on your own. Let's try to apply, let's say, a distributed load using the work equivalence system for this particular, let's say, beam. A distributed load having W. Let's analyze this beam. And this, as we just saw, this beam having a distributed load W can be represented by the nodal forces, as well as nodal moments, as well as nodal forces in this way. The sign conventions also has been taken into account. You are required to find the vertical displacements, as well as the rotations, as well as the nodal forces, and assume, in doing so, assume a constant EI value along the length of the element. Yeah. So what you do is you simply, in this case, since we don't have to consider two different axes of system, because the local coordinate system corresponds to the global coordinate system along the x-axis, we can simply skip the hat sign, as well as, of course, the hat sign, and use simple the signs without the hat to analyze this beam. So we define nodes. The two nodal degrees of freedoms will be like this, as I shown here, and this is the corresponding element stiffness matrix, which I have shown here. And you know, what you don't know at the moment is F1Y and M1. Yeah, but you really know the distributed load can be represented using these, let's say, forces as well as moments. So what you can do is you can simply apply this. So force at node 1 should be F1Y, but minus WL, because we know this distributed load has an impact, or distributed load when it is discretized can be has to have a contribution minus WL by 2 at node number 1. So F1Y minus WL by 2 has to be included. Similarly, the corresponding bending moment at M1, we know there's an additional minus WL squared by 12, which is due to the distributed load. So we know at node number 1, there should be N1, but this contribution comes from the nodal distributed load. Similarly, at node number 2, we know since it is free to move in this case, we know the only applied shear force and the bending moments are the ones which are given by the discretized formation of the where we have obtained the discretized values of the normal distributed load. So there are no additional terms acting, no additional bending moments or shear forces acting at this location. You simply substitute the values which you obtain from the discretization of the normal distributed loads. And once you substitute the boundary conditions at node number 1, there are no rotations because it's fixed. Once you substitute these boundary conditions and partition the corresponding, let's say, because these two values are 0, corresponded, once you partition these two equations, end up getting the corresponding displacement at node number 2 as well as the rotation at node number 2 by solving these equations. So you would end up, just try it on your own, partition this equation, the corresponding terms which you are interested in solving, substitute the boundary conditions, and you would end up in getting, let's say, negative transverse displacement, and of course in a negative rotation which takes place at the counter clockwise direction, which is also quite intuitive if you look at the figure. If you look at the figure, if such a force is applied, then of course the shear force or the transverse displacement force should be in the negative y direction, and of course the bending moment should also be in the anti-clockwise direction. So it's kind of like you have obtained a you will obtain a relationship for the transverse displacement as well as rotation using these parameters if you solve these equations. So so you can see that we have applied this relationship to obtaining global nodal forces, and you can include the values which you have just found now to analyze the total structure. These are the values you just found, and these are the let's say structural forces applying on the total structure, which is defined by, let's say, E in this case. You can solve this equation and simplify this, and you can find the total forces applying on the structure, which is given by these F1 and M1 values. So this also includes not only the forces acting on the given by the distributed load, but also taking into the reaction forces into account. These are the forces which will act on the total structure. So, you know, in order to when you do the correction, of course, in order to do the correction, you need to take out in order to find what are the exact values applied. You need to do a certain correction for the nodal forces, because there are certain contributions coming from the normal distributed force. You have to take these, you have to eliminate these accounts. These are the ones given by F naught here, the ones corresponding to the total distributed force. And since you already know the total forces acting on the structure, you negate the effects caused by the distributed force or distributed loads. The forces represented by the discretization. You need to take the effects of these forces out of this equation and find the vertical corresponding actual vertical reactions as well as moment at the specific locations. So you have to simply take out the forces or discretized forces in order to find the actual reactions experienced by the nodes at the corresponding locations. Yes, and at the end, in order to verify, you can take the force as well as moment equilibrium into account at the different nodes, and you can verify your answers whether the system is in equilibrium or not by writing down an equation. So with this, there's a lot of information. I was able to cover the beam section within this lecture. There's a lot of information. You will get more and more familiarized once you go through the lecture notes, as well as do more and more worked out examples on your own. So I will also upload some more worked out examples. Just try to get the concepts correct and try to do more and more examples so that you can get familiarized with these lessons. Let's wind up this session and see you next week. And let's try to discuss plane stress and plane strain conditions, and of course discuss about triangular elements which we can apply in the finite element method to tackle more complex problems. Thank you very much.